Alright, today we're going to learn fundamental theorem of calculus. This is another very important theorem in integration basically. This theorem has two parts. The first part is called fundamental theorem of calculus part 1. The second part is called fundamental theorem of calculus part 2. The first part is more theoretical and more abstract comparative to the second part. The second part is less abstract and less theoretical. All right. So directly I'm going to write down a fundamental theorem of calculus part 2. I abbreviate fundamental theorem of calculus by FTC. Okay. Fundamental theorem of calculus part 1. Give me a second. Fundamental theorem of calculus part 1. If f is continuous on the interval a comma b, then the derivative of this function gx equals integration from a to x f of t dt is f x. Okay, so that is the fundamental theorem of calculus part 1. This means here you have the function gx, which is given as integration from a to x f of t dt. The derivative of g is f of x, that is g prime x. I use g prime to denote the derivative of g, which is actually f of x. All right, so this is a very easy theorem, but here you have to keep your eye on some things. That thing is, make sure this is just x. This is just x. Okay, so if you are not allowed to keep x square here. Okay, you are not allowed to keep x square here. Let me take that down. Keep that in mind. You are not allowed to keep x square here. You are not allowed to keep some other functions like e to the power x, x square root of x. No, only thing that you can keep here is x. And then this is a function of t. This is a function of t, and then that is the integration with respect to t. All right. This thing is a function of x. This thing is a function of x. You know that. Once you integrated this part with respect to t, and then apply the upper limit and lower limit, the t will vanish. That's how integration works. When you integrate that, then you have to apply the upper and lower limit. Once you apply the upper and lower limit, the variable will vanish. Okay, so this right hand side do not have any t. The only variable in the right hand side is x. That's why I'm saying this is a function of x. Okay, g of x, a function of x, because right hand side will only have x after you have done the integration. All right, so let me take these extra things out. Keep that in mind. All right. Now let me explain another thing here. I will use green color for that. It will start from here. This is the start. You know, integration and differentiation are opposite operations. Um, let's say you are given a function, something like f of x. If you get the integration of f of x, you will get this thing, f of x dx. Okay, this is integration. Let me get more space here. This is integration. And then once you get the derivative of this right hand side, you can get the original function back. Okay, once you get the derivative of the right hand side, you can get the original function back. That's because integration and differentiation are opposite operations, like summation and subtraction, or multiplication and division. All right, so these are operators. Here the operators are integration and differentiation. Okay, let me take this out. That part is extra. All right. If you could understand this green part, you can easily understand this theorem. G of x is the integration of f of x. Once you get the derivative of the right hand side, you will get the left hand side, which is this. Okay, so you can just get this integration symbol out if you just get the derivative of the right hand side. All right. So go forward. Now we are going to discuss an example. This is the first example in this section. Example number 1. Use fundamental theorem of calculus part 1 to find g prime x of this integration from 1 to x 1 over t dt, where this x is positive. All right, so you have to find the derivative of g, that is g prime. All right, now I'm going to write g prime x is same as writing the right hand side like this. This is the derivative operator. And then here you have the right hand side of the given gx, the right hand side of that. All right, so that is 1 over t dt. All right, now go back to fundamental theorem of calculus. Here the only thing that you have to check is whether you have x as this upper limit, whether you have x as this upper limit. If you have x as the upper limit, you can directly use this result. Okay, you can directly use the theorem. All right, now you can see it is just x here. Okay, so it is checked. It is x. Here this should be a. It's a constant. It's a constant. So here this is 1. 1 is a constant. Okay, check. So the limits are okay, or upper limit and lower limits are okay. All right. So you can directly write the solution by using fundamental theorem of calculus. So this should be, if you had f of x here, sorry, if you had f of t here, the solution g prime x should be f of x. If you had f of t here, it should be f of x, the solution. Now here, the solution for this one should be actually fx. Okay, this is fx actually. What is f? F is this function. That is f of t. Here you have f of x, not f of t. So you have to replace t by x. You have to replace t by x. So the solution should be f of x should be 1 over x. That is g prime x. So that is the solution. So I haven't done anything fancy here. Only thing that I have done is I directly use the fundamental theorem of calculus. Okay. All right. Let's go to the second problem. Before going to the second problem, let me write down where I use the fundamental theorem of calculus. I use fundamental theorem of calculus when I move from that step to this step. Okay, so this is the place I use fundamental theorem of calculus. All right, move to example number 2. Use fundamental theorem of calculus part 2 to find g prime x of this gx should be integration from square root of x to 0, here sine t square dt. Okay, so this is the given problem. You have to find g prime of x. Okay, this is what you have to find. All right, so the things that you have to check is whether the upper limit is okay. Whether the upper limit is okay. For the upper limit, you need to have x. Okay, this should be x. Otherwise, you won't be able to use the theorem. This should be x. Okay, so that is not satisfied. And here, this should be a constant. Should be a constant. All right. So that's what theorem says. Here, this is, let me write something more here. That is the upper limit is just x and this is just a constant. Okay, that should be a constant. Now, nothing satisfied. This is the upper limit is also not satisfied. Lower limit is also not satisfied. All right. So we have to arrange the problem such that the limits are satisfied. All right. We have to just arrange the problem. Otherwise, you won't be able to use fundamental theorem of calculus part 2. The first arrangement that I would do is, let's see what happens if you switch the limits. If you switch the limit. Alright, so what I'm going to do is switch in the limits. I write integration and then I switch the limits. Here I have 0, here I have x, and then I write sine t square dt. Since I switched the limits, I have to introduce a negative sign in front. That's a law, if you can remember. Okay, that's a law. So I'm going to write the law here. You learn this in definite integration. In the lesson of definite integration, you learn this. Let's say you're going to integrate f of x from a to b. If you switch the limits, that means you are integrating from b to a, the same function. Then you have to introduce a negative sign in front. Okay, that is what I have used here. Alright. Now again check lower and upper limits. Here the lower limit is fine because it's a constant. But the upper limit is still not right, because upper limit should be just x. See, the upper limit should be x. The lower limit should be a constant. So we have to work more to get the upper limit. All right. Now what should I do? So in this case, what I'm going to do is I'm going to use a substitution. The substitution is u equals to square root of x. Because this is square root of x, I have to get rid of that square root of x and then put a variable like x or maybe like u. Okay, so let me get out that circle. Right. Here the substitution that I make is u equals square root of x. Substitute this is what you're going to substitute. Since you're going to introduce a new variable, you have to change most of the variables in this problem. All right. So u will be a square root of x, and then you have to change this variable in few more times. First of all, let's get the derivative of u with respect to x. I will explain why I do this, because I need that later. Okay, get the derivative of that. I'm sorry, I made a mistake here. Yes. Yeah, I think I'm fine. Okay, let it go like this. Before introducing this thing, let me get some space here. In this problem, you have to find the derivative of g. Derivative of g means this thing, d over dx integration from 0 to square root of x sine t square dt. I forgot to write that step. All right. So you have that step here now. And let me push this a little bit up. The reason that I wrote this quantity, this function, is that's what we need, right? That's what we need. So g prime of x is actually, you just put this thing inside this d over dx operator. That's the derivative operator. All right. and then get this derivative du over dx. I will explain why I do that. This is the power law. You have to use the power law here. Power law for the differentiation. If you can't remember the power law for the differentiation, that should be like d over dx x to the power n. This should be nx n minus 1. Alright, so this should be n. Here you have n, here you have half, so you write half x to the power, here n minus 1. N minus 1 is half minus 1. Then this should be 1 over 2 times the square root of x. That is actually du over dx. Alright. Now I'm going to make a small arrangement. I take this as equation number 1, and then I'm going to use the substitution for equation number 1. By 1, I write g prime x should be here. First I write what I have right now, and then I will modify that. Integration from 0 to square root of x. Here you have sine t square dt. Alright, so since I'm going to introduce a new variable u, I use the chain rule here. In this chain rule, what I do is I just take this dx part out, and then I write that dx here, and then I write du here, du there. Alright, you can see this du can be cancelled by that du, and you can bring that one over here. So that is what is given there. Alright, so that's how chain rule works. You can just cancel them and then get the original expression. Alright, so go forward. And now I explain why I did compute that quantity. That quantity is actually this. Alright, that quantity. You can just substitute that quantity here. And then this is actually u. Your new variable is u. Alright, go forward. I write d over du, and for square root of x I write zero. For square root of x I write u, because that is my substitution. From here to there, there's a change. And then I write sine t square dt, and for that part du over dx I write 1 over 2 square root of x. Alright, there's a change from here to here. That change is supported by equation number 2 by 2. By 2. All right. Let me rearrange this. I write 1 over 2 times the square root of x here, and then I write that negative here, and then I write d over du 0 to u, integration from 0 to u, sine t square dt. All right. Now just concentrate on this part. Just concentrate on this part. Here the variable is u. Don't worry about that. In original equation, the variable is x. In original fundamental theorem of calculus, the variable here is x. All right. Don't worry about that. Now our new variable is u. Okay. Go there. Here this is a constant. This is a constant. That means check. This is just u, check. Okay. This is a constant, lower bound, that's u. U is fine because our new variable is u. Let me write that. Keep in mind that our new variable is u, not x. Okay, our new variable is u. U here and u there. We have to make sure the upper limit is just u, the lower limit is a constant. Now we can directly apply the fundamental theorem of calculus. Then this equals 1 minus 1 over 2 times the square root of x, and for the green part I write f u. Okay, fu. Now I have to show you what is f. F is actually the function inside. F is this function actually. All right, you know that already. This is f of t. That was f of t. Go back. See, this inside function is actually f. Okay, that function is actually f of t. Now that function is actually f of t. All right. But here you have to write f of u, that the variable, u is the variable. Go back to fundamental theorem of calculus. See, here function is f of t. Here you wrote f of x. Here you wrote f of x. That's how fundamental theorem works. Now I wrote f of u, and then f of u is, let me write that, minus 1 over 2 square root of x. F of u is actually sine u square. How did you get from here to here? That is because you know ft equals sine t square. Alright, now the thing is original variable. Here the given original variable is x. U is a variable that you introduce. Right? You have to get rid of u. Original variable is x. U is what you introduce. So I have to get this u out. For that you have to substitute back. Now I have to substitute back. This should be minus 1 over 2 times square root of x, then sine u square. U here, that u is that, u square is just x. That is sine x. Y because u equals x square of x, square root of x. All right, so this is actually g prime x. This is actually g prime x. All right, if I'm going to write down the place where you use fundamental theorem of calculus, that is this step. From here to here you used fundamental theorem of calculus. Part 1. All right, so that is the second example. The first example was really easy because that is just straightforward. Example number 1, which was easy because that's a straightforward example. And the second one is kind of required some work to be done. Okay, second example requires some work. Now move to example number 3. Example number 3 is even different than example number 1 and example number 2. Example number 3. Compute integration from compute the derivative of the integration from x to x squared plus 100, and here you have cos t dt. All right, so the same thing, you have to check upper and lower bounds. The lower bound is not a constant and upper bound is not x. Okay, both bounds should be rearranged. Both bounds are not working. So let's see how to work on this problem. Okay, first of all, I'm going to rewrite the problem. This is what is given to you. X to x squared plus 100, then cos t dt. All right, now what I do, I just split the I just split this part, the integration part. I'm going to split that integration part. There's a law for that. There's a rule for that. I will explain that rule here. Okay, so I'm going to explain that rule right here. You can remember this rule. Let's say you are going to integrate something from a to b. You're going to integrate something from a to b. But you can just split this integral into two integrals, from a to c and then from c to b. All right, so you can do this thing. There's a law that you learn in definite integration lesson. All right, so I'm going to use the same rule here. Let me take that out. So you could split this. First of all, let me write d over dx part. Once you split this, you can write like x to 0 cos t dt, 0 to x squared plus 100 Alright, so this is what I'm saying is this part, this split is supported by this green color block. Now go forward. I'm writing this is d over dx. You can distribute that derivative operator to this part and into that part. That's what I'm doing right now. Okay, I'm going to distribute this differentiation operator. You write d over dx and then integration from x to 0 cos t dt and then plus d over dx integration from 0 to x square plus 100 cos t dt. Just consider this as part A and consider this as part B. Okay, so I'm gonna simplify A and B separately. I am given this problem, which is just a single problem. Now I split that into two problems. Okay, I split the given problem into two problems. So I'm gonna work on each problem separately. All right, give me a second. All right, go forward. Let's work on part A. In part A, you have to compute this derivative, integration from x to 0 cos t dt. Okay, now you have to check lower and upper limits. Lower limit is x, not okay. Upper limit is 0, not okay. And now you have to arrange lower and upper limits. The trick that you could use here is just switch the limits. Okay, just switch the limits. Once you switch the limits, you could write this as 0 to x cos t dt. Since you switch the limits, you have to introduce a negative sign. All right. Now you can check the limits. 0 is a constant, okay. X is just x, okay. Okay, so that's fine. Then you can directly use fundamental theorem of calculus. This cos t is the function ft. If you use the fundamental theorem of calculus here, if you want to see the fundamental theorem of calculus again, go back. This is fundamental theorem of calculus. This is fundamental theorem of calculus. Here you have ft and here you have f of x. The derivative of g, where g prime x should be f of x. Alright, give me a second. Alright, great. Now you write this to be, this negative sign comes in front and then you write f of x. You know f of t is cos t, then this should be minus cos x. That is the solution for part A. Take that as 1. Okay, now move to part B. Now, if you want to, if I want to show you the place where you use fundamental theorem of calculus, that is this step. This is the place where I use fundamental theorem of calculus. Now this is part 2. Part B. In part B, you have to get derivative of this thing. It is integration from 0 to x square plus 100 cos t dt. Alright. Now check the limits. Lower limit is fine. Upper limit is still a problem. Upper limit is a problem. Upper limit is supposed to be x. Okay. Now what should we do? Just use u substitution like we did before. I'm going to use u substitution here. I take my u to be, give me a second, substitute u equals x square plus 100. Okay, first I get the derivative of u because I need that later. Du over dx equals 2 times x. Okay, now let me rewrite the given problem, which is d over dx integration from 0 to x square plus 100 cos t dt, and this equals, I'm going to use the chain rule here. Okay, so I have dx here. I'm going to push that dx to the end. Let me rewrite that. So I write this as integration from 0 to x square plus 100 cos t dt. And what I'm saying is I'm going to push this dx to over there, and then here I put du, here I put du. Okay. You can simply see that this du can be cancelled by that du. And then you can bring this dx over here. So this is that right hand side, then same as left hand side. Right, then you can write this to be d over du, and this upper limit can be replaced as u. Integration from 0 to u cos t dt, and here du over dx. This part du over dx, we have already found that that's 2x. Alright, see, it is 2x. So this should be 2x. Let me get a little bit of space here. And let me get more space here. Oops, sorry. All right. What I want to say is there's a change from here to here, and then this function, and there's wait a minute, there's another change from here to here. All right, and this function is actually f of t. Now I use fundamental theorem of calculus. You just write f of u. Alright, and then here 2x. Okay, let me write that. This is the place where you use fundamental theorem of calculus. Part 2. I'm sorry, part 1. Let me check something. This should be part 1. I haven't taught part 2 yet. So let me write this. F of u should be cos of u 2x. Reason for that is f of u equals let me write like f of t equals that is cos t. All right, the thing here is you can keep the variable u, because the given variable is x. You have to get all the extra variables to the original variables. You have to get rid of this u, right? For that you could use this function. Right, so this equals cos u should be x square plus 100 times 2x. What you use from here to here is the substitution. U equals x square plus 100. And finally I write this equals 2x cos x square plus 100. Take that to be part 2. That's you found the solution for part A, which is right here. You found solution for part B, which is right here. Now you have to just sum them up. Right, you have to sum them up. Let's take this as this. Let's denote this equation as asterisk. Okay, now I'm going to substitute 1 and 2 to the asterisk. Substitute into this asterisk. Then you get the given then you get the solution to the given problem. Let me copy the given problem. So that's the given problem. Give me a second. Oh, I think it didn't copy well last time. Let me copy it again. I want to copy that part. Copy. Go to insert. Paste. It works good. That equals 1 plus 2. That means 1 means minus cos x plus 2 means 2x cos x square plus 100. Alright, so that is the solution for the given problem. Alright, so we discussed three problems, three diverse problems for fundamental theorem of part 1. Now it is the time to go for fundamental theorem of calculus part 2. Alright, part 1 is completed, so now we are going to fundamental theorem of calculus part 2. Actually, fundamental theorem of calculus part 2 is easy. It is easy, and the other thing is it is something you already know. Alright, fundamental theorem of calculus part 2 is already know, something already know. Alright, fundamental theorem of calculus part 2. Okay, theorem. If f is continuous over a comma b and f, this is uppercase F, is an entire derivative of f on AB, then you write integration from a to b f of x dx is uppercase F of b minus uppercase F of a. This is called fundamental theorem of calculus part 2. This is something you already know, right? So this is just indefinite integration, right? So let's say this is the given problem to you. So you have to integrate f of x from a to b, and then you just integrate that. Let's say this b, uppercase F is the integrated function. Okay, the uppercase F is integrated function of this lowercase f. And then what you do, you just substitute the upper bound minus substitute the lower bound to f. Alright, so that's something very easy and something you know already. So that is actually fundamental theorem of calculus part 2. Alright, directly move to examples. Example number 4. In this example, you have to integrate this function 1 plus cos 2t over 2 dt from pi over 2 to 0. Okay, this is what you have to integrate. Now you have to memorize those properties or the laws of integration. All right, so the first law that you could use is this is called the integrand. Integrand has two functions, two separate functions. You can get the integration of those two functions separately. So what I write here, integration from pi over 2 to 0, then you write half here plus cos 2t over 2. So this is what is given to you, and then I'm going to integrate each separately. First I integrate half, and then I integrate cos 2t over 2. This half is a constant. That's another property. You can take constants out, and then this is dt, and here also half a constant. You can take that out, and then here integration from pi over 2 to 0 cos 2t dt. Okay, the integration of this part is straightforward. That's the power law. So you write half, and the integration of here you have, technically you have 1 here. Okay, 1 to the power, you have 1 here, I'm sorry. You have 1 here, 1 is same as, this 1 is same as x to the power 0. Okay, 1 is same as x to the power 0. Then if you use the power law, if you can't remember the power law, I'm going to write it maybe here. The power law for integration. Let's say you have x to the power n dx. The integration of that one should be, x to the power x to the power n plus 1 over n plus 1. Okay, this is the power law for integration. Now this should be x to the power 0 plus 1 over 0 plus 1. And you have half here. And then how do you integrate cos 2x? You can't integrate cos 2x directly. You can't. For that you have to use a trigonometric identity. I can remember, I don't know whether you can remember that. There's a trigonometric identity that you could use here. In this case you can go forward and directly integrate that. You can directly go forward and integrate that. Okay, let's integrate that. So let me take that out. And the integration of this one is actually sine 2t divided by 2. Alright, so you have to apply the upper and lower limits. It is pi over 2 to 0. And here upper and lower limits are pi over 2 to 0. If you are not sure whether you get this after integrating that, you can check it again. If you are not sure whether whatever you got here is correct, you can check it back. How do you check it back? You just get the derivative of that. Get the derivative of this. Get the derivative of that and check whether that is same to this. Okay, you can check it back. Now I'm going to check it back for you. Let me put a small note here to check this is correct. Differentiate and check whether you can get okay. So this is the experiment you could do. So that's what I'm doing right here. I'm gonna differentiate sine 2t. I'm going to differentiate sine 2t over 2. So like you can take 2 half. You can take half out and then differentiate sine 2t. If you differentiate sine 2t, it should be cos 2t times the chain rule 2 comes. Alright, so this should be, you can cancel this 2 with that 2. This is cos 2t. That is whatever you have here, right? That is whatever you have here. That means the derivative of this one will give you this. Derivative of this one will give you, that means this integration is correct. You can always check whether that's correct. All right, go forward. And then you have to apply the limits now. Here you have, sorry, let me take blue pen. Here half, and then apply the upper limit, which is pi over 2. Apply the lower limit, which is 0, plus 1/4. Apply the upper limit, sine 0, minus, apply the lower limit, sine pi. Okay, here this should be half, multiplied by pi over 2 is directly pi over 4. Actually, I made a small mistake here. I have to switch these two. Values. It should be 0 minus pi over 2, because upper limit is 0, lower limit is pi over 2. It should be 0 minus pi over 2. Alright, then here you will get minus pi over 4. And from this part you get plus 1 over 4. Sine 0 is 0. Sine pi is also 0. Alright, so if you simplify this, what you get is minus pi over 4. That is the solution. Let me move to the next problem, which is example number 5. You have to integrate from 3 to 6, 1 over x dx. Alright, this is easy. There's a direct formula for that, which is ln x. Then you have to apply the limits, lower and upper limits. Alright, then you have to apply the upper limits using fundamental theorem of calculus part 2, which is ln 6 minus ln 3. By the way, I forgot to tell where you use fundamental theorem of calculus. In the previous problem, the places where I use fundamental theorem of calculus are here. So this is the place where I use fundamental theorem of calculus part 2. Here you use fundamental theorem of calculus part 2. And again, here you use fundamental theorem of calculus part 2. All right. Now you're going to simplify this. Now you have to memorize the laws that you learn in logarithm, which is in calc 1. Here you have subtraction between two ln functions. You can write that as a division. If you can remember that law says log a over b is same as log a minus log b. Here I have ln. This rule holds for every base. Base can be e or base can be any number, any base. Okay, this log works for any base. What is ln? Ln is actually log to the base e. Let me write the base too. Here the base should be any base. I'm sorry. Let me put the base as here a over b. Let me put the base as maybe k. It works for any base. ln means log to the base e. You know this thing. ln is same as log to the base e. All right. If this is given to you, you can get the right hand side, or if that is given to you, you can get the left hand side. You can go back and forth from left to right, right to left. Now you write this to be 6 over 3 is 2. You write this to be ln 2. So that is the solution. All right. So that is the end of the section. In this section, we learn fundamental theorem of calculus. There are two parts of fundamental theorem of calculus, part 1 and part 2. Part 1 is more theoretical than part 2, and also part 1 is little bit more abstract than part 2. Actually, part 2 is something you already know. Okay, in part 1, this is the corresponding theorem. This is the corresponding theorem. You have to always check these limits, x and a. You have to always check these limits in a given problem. If they are satisfied, then you can directly use the theorem. If they are not satisfied, then you have to rearrange the problem such that it satisfies these limits. Okay, we discussed 3 problems. The first problem is easy, and the second problem is little challenging, and the third problem is highly challenging. Okay, then we move to a fundamental theorem of part 2. Let me put this in a box. And then we move to fundamental theorem of part 2. Fundamental theorem of part 2 is something you already know. It explains like just get the integration of the function and then apply the upper limit and the lower limit. All right, that will give you the solution. Here we discuss 2 problems. Example number 4 and example number 5. Okay, so this is the end of the section. Thank you very much.